Hi everyone, welcome to my channel Essentials of Electronics. We'll be discussing about transistors, the different types of transistors and their biasing circuits. The transistors I have taken here is BJT, FET. Under FET we have two types, JFET and MOSFET. First we'll discuss about BJT. The full form for BJT is bipolar junction transistor. This BJT has two types of configurations. One is NPN and the other one is PNP. So during fabrication, P-type semiconductor is patched between two N-type configurations. So framing NPN configuration. Examples for N-type semiconductor are silicon and germanium. Examples for P-type semiconductors are phosphorus. Similarly, patching a N-type semiconductor between two P-type semiconductor layers form PNP configuration. Then, how do we classify or how do we realize the symbol of BJT? Now, I'll show you the symbol of BJT. The BJT bipolar junction transistor has three terminals: base, collector, and emitter. The arrowhead moves away from the base, meaning the current moves from the base towards the emitter terminal. This is considered as the symbol of BJT. I'll draw the symbol of PNP as well. Base, collector and emitter, the arrowhead moves, which means the current moves from the emitter terminal towards the base current. Here we have three currents, namely the current flowing into the base is called the base current, the current flowing into the collector terminal is called the collector current, and the one flowing through the emitter terminal is called emitter current. The next topic is we'll be discussing about the basic biasing methods of BJT. There are different types of biasing in BJT. Number one, base bias with emitter feedback, base bias with collector feedback, emitter bias, and voltage divider bias. So we'll be discussing these types of biasing. First of all, what is biasing? Yes, the process of supplying suitable voltage to the semiconductor device along with its associated components is called biasing. So we'll discuss how to lay out a proper biasing for a BJT under base bias. So now I'm going to draw a base bias circuit using BJT. So we'll be drawing, I have taken the NPN configuration only. We have to give proper biasing, isn't it? The biasing along with the suitable resistors connected to the BJT is called proper biasing circuit. Here we have VCC supply. I'll name the terminals base, collector and emitter. The emitter terminal will ground the emitter terminal, and I have connected two resistors. This resistor connected to the collector terminal, let me name it as RC. The resistor connected to the base terminal, let me name it as RB, base resistor and collector resistor. And let me show the currents flowing in the circuit. Here we have VCC, this is IC current, and here we have IB current. Okay. Now with respect to this, it is possible for us to write equations for this circuit. I'll just mention the names of the currents. The current flowing in the base terminal is called base current. The current flowing in the collector terminal is called collector current. Now, using Kirchhoff's voltage law, it is possible for us to frame some equations, put those equations into the circuit, and try to find the value of IBIC or RBRC. You can design the value of the resistors yourself with the help of applying KVL into the circuit. The first one, applying KVL in the outer loop. This will consider as the first loop and this will consider as the second loop. This is called the inner loop because we are feeding the input to the base terminal. The collector emitter terminal is called the outer loop. Here I hope the emitter terminal is grounded here. So this configuration is called common emitter configuration. If the base terminal is grounded, then we are supposed to call it as common base. The collector terminal is grounded, it is called as common collector terminal. Now the most of the examples I'm going to take here is common emitter amplifier only because it shows more amplification compared to the other counterparts, common base and common collector. Now let me write the equation in the input loop. The voltage drop across the RB, and here we have a particular voltage called VBE where the voltage across the base and the emitter is called VBE. So applying KVL, IBRB plus VBE will be equal to the total constant voltage. Now it's very easy for us to determine or design the value of RB. Yes. Now RB is equal to VCC minus VBE divided by IB. This VBE is a very small value. For example, if it is around 0.7 volts and the voltage that is going to be applied here is going to be plus 12 volts, it may be plus 9 volts, or it may be plus 24 volts. Compared to these voltages, 0.7 volts is very minimum, and hence we can tell that RB is equal to VCC divided by IB. And now let me try to write the equation of collector current or RC. So we need to apply KVL in the outer loop. The voltage drop across ICRC and VCE is equal to the total voltage VCC. So ICRC plus the voltage drop across the collector emitter is equal to VCC. This VCE may be considered as the output voltage in our common emitter configuration. So to design the value of RC, now we have VCC minus VCE divided by IC. And also IC is equal to VCC minus VCE divided by RC. If we know the values of RC, it is very easy for us to calculate the approximate value of the collector current. So this is a proper biasing done. Now what we have gone through so far is we have determined the value of RB and RC in base bias circuit. The second type of biasing what I am going to go through is emitter feedback bias. What is emitter feedback bias? So it's almost going to be the base bias circuit connected to an emitter resistor. Yes, a collector terminal, base terminal, and an emitter. In your emitter terminal will be connecting an emitter resistor. So how many resistors do we have here? We have 3 resistors connected, one each to the 3 terminals of the BJT. And the circuit goes this way. This total supply voltage is going to be plus VCC. Now we'll mark the current directions. It's going to go like this: collector current, the base current, and the emitter current. Okay. Now let us try to find the value of IB, IC, or IE. So this is emitter feedback bias. This type of biasing is emitter feedback bias. Now we'll try to find the value of IB. So it's going to, we are going to apply KVL in this loop. So the drop across IBRB, here we have a drop. What drop is that? The voltage drop across VBE and the drop across IERE. So I'm going to write the equation related to the determination of IB. So in the inner loop, this I'll consider as a first loop. In the first loop, I'm writing the equation IBRB plus VBE plus here we have an emitter resistor in the emitter terminal. So that is also considered here. So 3 voltage drops we have here, and as I told you in the last slide, this VBE is around 0.7 volts, which is almost negligible. So we could almost neglect it. So finding the value of IB is VCC minus IERE divided by RB. This is the value of the input base current. And now next we'll try to find the value of IC. So this base current IB is with respect to the involvement of the resistor RE. And now let us try to find the value of IC. So how will we try to frame the equation for that? The drop across ICRC, the drop across VCE, and the drop across IERE is equal to total VCC. I'll try to write the equation here. ICRC plus VCE plus IERE is equal to the total voltage drop. So you can find the value of any kind of resistor or the value of the current. I take, since collector current is considered as the output current, I'll try to determine the value of collector current, which is going to be VCC minus IERE minus VCE. VCE is said to be called as the output voltage, the whole divided by RC. Now thus we have determined the value of IB and IC in emitter feedback bias. Yes. Now I am moving into the third type of bias, that is base bias with collector feedback. So what do we do with that? We have a collector terminal, a resistor to be connected in the collector terminal, which will be behaving as a feedback resistor. So we'll try to complete the biasing circuit of collector, emitter and base. Yes, this the resistor connected to the base terminal B RB, the resistor connected to the collector terminal B and RC, and we don't need to connect any resistor in the emitter terminal. So what would be the values of the currents flowing here? When we supply a plus VCC constant voltage, some amount of current flows in this path. That current is the total current. Yes, that current, let us consider that as IT, and it splits up into this current flowing into the collector terminal BIC and the current flowing into this base terminal BIB. So what is the total current? What would be the name of the total current here? The total current is IB plus IC. This total current contributed by supply VCC is IB plus IC. Now we'll try to write the base equation for IB. IB is equal to VC minus VBE divided VCC minus VBE divided by RB. Yes, let's assume that IC is very much greater than IB, then the collector voltage VC will be equal to VCC minus ICRC. Right? So then substituting this value, we will be able to get the following equation. the collector voltage VC will be approximately equal to VCC minus ICRC. So thereby substituting in the previous equation, also we have IB is equal to IC divided by beta into DC, where beta is the current gain of the circuit. So substituting for VC in the above equation, we'll be getting IC divided by beta DC is equal to VCC minus ICRC minus VBE divided by RB. Then we could also solve for IC, where IC value will be equal to VCC minus VBE divided by RC by RB divided by beta DC. Since the emitter is grounded, VCE will be equal to VC. Thereby, we will be getting VCE is equal to VCC minus ICRC. Yes, these are the equations with respect to base bias with collector feedback. Then we are moving into the fourth type of biasing. It is emitter bias. Kindly bear with my handwriting. I'll try to draw the circuit of emitter bias. So what do you mean by emitter bias? The emitter terminal should be biased, meaning we are going to give a separate voltage. We are going to give a separate supply voltage with what potential? Negative potential being connected to the emitter terminal. Yeah, it's going to be like this. I am connecting a resistor R to the terminal base, a resistor RC to the terminal collector terminal, supplied with plus VCC supply voltage. So we have three resistors RC, RB and RE. The emitter terminal being supplied with negative voltage, where the other terminal is to be grounded. I'll try to mark the currents flowing in the circuit. The VCC supplies current IC, IB flows into the base, and IE along with the component VBE. Yes. So this is the emitter bias circuit. The emitter terminal has been biased along with the biasing voltage of VCC connected to the collector terminal. And now we'll try to write the equations for the above circuit. The emitter voltage VEE plus IBRB plus the base emitter voltage plus IERE is equal to 0. As we know, IB is equal to IE divided by beta, the current gain, and the transposing VEE. So we'll try to solve it like this. IE divided by beta DC, IE divided by beta DC into RB plus IERE plus VBE is equal to minus VEE. So factorizing out IE and solving for IE in this equation, we will be ending up with the equation to find out the value of the emitter current. It is minus VEE minus VBE divided by RE plus RB divided by beta DC. Also, the collector voltage with respect to the ground is Vc is equal to Vcc minus ICRC, and Vb is equal to VE plus VBE. And these are the designed analyzed equations from the emitter bias circuit. Now we have gone through the different types of biasing. Out of 5 types we have discussed 4 types of biasing: base bias with emitter feedback, base bias with collector feedback, and this one we are ending up with emitter bias. The other types of biasing we'll try to discuss in our next video. Thank you.